All right, let's try that last one again. We're going to integrate 2x raised to the power 7 plus 6x plus 5 using more of how we're going to do these, which is the term-by-term integration technique. So this is going to be kind of a more accurate reflection of the work and the thought process of how we're going to do these. So, you know, we don't generally show, we did this one before, we don't generally show all of this, especially like the sum rule and the constant multiple rule. We kind of do these steps in our head. So let's think about how this might look if we were going to kind of do this one generally, how we actually do it. All right, so when we look at this function, kind of what we're seeing here is there's three separate terms. There's this 2x raised to the power 7 term. There's this 6x term. Let me box these in. And there's this plus 5 term at the end. So when I look at this, the plus signs, and as we're going to see subtraction signs, they kind of split up our function into different distinct pieces. And that's, or what we call terms. And that's what we're going to do here. So we have three separate terms. And what we're going to do is just start with the first term, integrate it. Then move on to the second term, integrate that. Move on to the third term, integrate that. And we just kind of go down the line. However many terms we have, we just go down and integrate them all. And so when we have power functions like this, the first thing we want to do is just, if applicable, rewrite each term so that it's in a good format for integration. So constant a times the power function x raised to the power r. And we see that we have that already here. And so we're just going to integrate each of these terms. So let's start with 2x raised to the power 7. And what's helpful is identify just the variable part. So why it's helpful is we're just going to focus our attention on just that variable part. Get the antiderivative. So x to the 7, what's the antiderivative? Well, it's going to be x raised to the power 8. Take that new exponent 8, flip it, put it in front. And then that 2 is a constant multiple, so it just stays in front. All right, so there we go. We have our antiderivative for this first term. Then we go on to the second term. And we have a plus sign in between, so we're going to have a plus sign in our antiderivative. So kind of the last part of this term-by-term integration is as we move from term to term, we just keep the original addition or subtraction signs. So here our function originally had a plus sign. We're going to keep a plus sign. All right, so we're on to the second term now. It's a constant multiple of 6. And so we want to find the antiderivative of the variable part there, the x. So that's just another power function. So our variable is x. We add 1 to the exponent. That's going to bump us up to 2. Take the 2, flip it, put it in front, so 1/2. We're done integrating this piece, so now we're ready to move on to the next term. And there's a plus sign there, so we keep a plus sign down in our antiderivative. And then we find the antiderivative of 5. And that's just a constant function all by itself, so it's 5 times x. And then once we get to our last term, very last thing we do then is plus c at the end. And then, you know, you might even do some of this in your head to kind of even skip ahead a little further, but this is fine. But maybe then you get 1/4 x raised to the power 8 plus 3x squared plus 5x plus c. There we go. All right. Well, so that's how this term-by-term integration works. Let's try another one. 5x to the 4 minus 4 over x cubed. Now, when we look at this, what I'm seeing is I'm seeing two terms. Here's my first term, here's my second term, and then they're separated by a subtraction sign. So I'm just going to go term by term, integrate each of these. Now, when I look at this, though, this 4 over x cubed, it's not quite good enough yet. We want to write it as a constant times a power function. So before we go further, I'm going to rewrite this function. The 5x to the 4, perfectly good. This thing is that term is ready to integrate. It's this 4 over x cubed that we want to do a little bit of work with. So I'm going to rewrite this as minus 4x to the minus 3. Minus because we had subtraction. 4 is our constant multiple. And then, if we wanted to, we could really think of this as 4 times 1 over x cubed. And then instead of 1 over x cubed, that's just x raised to the minus 3. All right, so there's our function. And now when we look at this, each of these is in a good format for integration. So each of these is in that correct format of a times x raised to the r. That's what we want. Something we can actually integrate. All right, so now we're ready to go and do it. So when we just focus our attention, zoom in on each term. So we're going to focus our attention on this 5x to the 4. And really we can zoom in further and just focus our attention on that variable part. So the antiderivative, 5 is a constant multiple, so it just stays in front. And then integrating this x to the 4, variable is x, add 1 to the exponent, so that bumps us up to 5. Take this new exponent, flip it, put it in front, it's 1 over 5. And we're done for that first term. So now we go on to the second term. There is a minus there, so we're going to have a minus, we're going to have subtraction. Constant multiple 4 just stays in front. And now we're going to focus our attention on just getting the antiderivative for that variable part. Variable is x. Add 1 to the exponent, so we go from -3 up to -2. Take this new exponent of -2, flip it, put it in front, so -1/2. And then we've just finished integrating our last term, so plus c at the end. And then we just simplify. And again, you might even, once you get the hang of these, you might be able to get the simplified answer right away without even showing this step. So 5 times 1 over 5 is 1. We get x raised to the power 5. -4 times -1/2 is positive 2. So we have positive 2 times x raised to the -2, and then plus c. All right, so this is term-by-term integration, and it's really nice. Now, the nice thing about integration is we can always check our answer. So this goes beyond term-by-term integration. This idea of being able to check our answer, we can do it for any integral that we can calculate. And the way you check your answer is you start with your answer and you differentiate it. So for instance, if we wanted to check this, maybe we get the power rule right or something like that, we can start with our answer. So x raised to the power 5 plus 2x raised to the -2 plus c, and we can just differentiate this. And when we differentiate, the way we differentiate, we just go term by term. So let's start with this x to the power 5. Differentiate it. What do we get? We get 5x to the power 4. So here we're using the power rule, but now we're using the power rule for derivatives. So it might get a little confusing. So just make sure if you're differentiating, you do the power rule for derivatives. If you're integrating, you kind of do the opposite. You do the power rule for integrals. All right, so that's the derivative of the first term. Now we go on to our second term, differentiate this. So I take the -2, bring it down, multiply it with the 2 that's already there. I get -4. And then I subtract 1 from the exponent. So I go from -2 down to -3. And then derivative of constant c is 0. And if this was the correct answer, when we differentiate it, I should get back my original function. And that's what we're seeing here. This is our original function. 5x to the 4 minus 4x to the negative 3. So if you take your answer, differentiate it, you should get back where you started. So we can always check. Which is nice. All right. You don't have to do this, but if you're uncertain of your answer, this is not a bad thing to do. And really what we're doing here is what we mentioned when we first introduced this idea of antiderivatives. Go back all the way. Start at the very beginning. Oh boy, we did a lot. Here we go. What did we do? When we first started talking about antiderivatives, we said 1/3 x cubed was the antiderivative of x squared. How did we check it? Well, we took that 1/3 x cubed, we differentiated it, and got x squared. We also checked 1/3 x cubed plus 1. Differentiated that, saw we also got x squared. So that's all we're doing in this last example here, is we're just using differentiation as a way to kind of check our answer. So we're starting with our answer, differentiating, and seeing that we get back the original function. All right. So we'll be trying a few more examples, but so far everything we've done has x's in it. We can use other variables. So we're just going to make a note of that next.